Good afternoon, friends. So far, we have discussed constants, variables, literals, and the different types of expressions, data types, arrays, types of arrays, and the where reserved word in Java. In this session, we focus on the rich set of operators in Java. Java provides some rich set of operators similar to the powerful operators from C and C++ languages. Arithmetic operators, bitwise operators, relational operators, logical operators, ternary operator. Some of the operators are additionally supported in Java compared to C and C++ languages, and most of the operators are behaving same as that of C and C++ languages. Now let us explore the first one, arithmetic operators in Java. Plus, minus, star, slash. These are the basic arithmetic operators. In this plus minus sources, unary plus, unary minus. Likewise, binary plus and binary minus. You know, unary operators. What are unary operator? Unary operator takes this general form. OPR, then apparent. What is OPR? OPR assumes any of the values from the set minus comma plus. Minus is also said to be the unary minus operator. Plus is said to be unary plus operator. In this case, suppose int x is equal to minus a or minus b, int y is equal to plus a. Here, what is the minus? Minus versus unary minus, because minus is the operator and q is the apparent. Likewise, int y is equal to plus a, and this plus versus unary plus. Following that, the operand is available. Operand is a. Then star multiplication slash division. With respect to the integer operands, integer division is carried out, and with respect to floating point or double operands, floating point operation is carried out with respect to the division. Percentage operator similar to the C++ percentage operator, which returns a reminder after performing the integer division. Where in Java, the percentage operator can also be applied to the floating point types we see. Then plus plus and minus minus, increment and decrement operators. Plus plus, right? Pre-increment or post-increment. Pre-decrement, minus minus are a post-decrement operation. Plus is equal to, minus is equal to, star is equal to, slash is equal to, percentage is equal to. These are the shorthand assignment operators. So writing x is equal to x star 5 means, in short, we can write this as x star is equal to 5, similar to C++ type. Likewise, minus is equal to star, plus is equal to, slash is equal to, percentage is equal to, right? Can be written in the shorthand format. Now let us explore these operators. Let's consider this example. X is declared one integer variable having a value 100, and y is declared 125.25 as a floating point quantity. So if is mandatory one because y is a floating point variable. Now we like to perform the integer arithmetic as well as floating point arithmetic, right? So we like to perform the integer division. X by 3 is plus x by 3. What is the value of x by 3?
33.
23.
3 without a decimal point, because x is an integer 1, 3 is an integer 1. In the integer mode, x by 3 is evaluated and the result is printed. Likewise, y by 5. But what is y? Y is a floating point quantity, right? So 125.25 and 5 is integer mode, 125.25 in the numerator divided by 5. Now type promotion rules are applicable. 125.25 double quantity, floating point quantity, 25 uh, denominator 5
25.
into 5.0 f. So floating point quantity. So floating point arithmetic is carried out. The corresponding quotient is returned. Yep. Okay. Now 1000 division 50. 1000 division 50. Right? What happens? Corresponding integer value is returned. In this case, 1000 division 50.0. 50.0 by default double quantity. So this is a double operand. Numerator is an integer one. Integer by double, right? This is converted to double by double. Double is a result. Likewise, 100 by 3.0 f. 100 is an integer one. This is a floating point quantity. So the result is a type promoter to floating point quantity. Here same as the top, right? Double division integer by double. The result is type promoter to double one. Operators 1, Java C, operators 1 dot Java. Java operators 1. This is the result, right? X by 333, Y by 5 is 125.05, sorry, 25.05. Then the integer division, the floating point division, double division, the operations are carried out and the result is printed. Having any queries in this integer division as well as floating point division? If the operands are of completely integer mode, then the integer division is carried out. Integer by float, result is in a floating point operation. If float by double or integer by double, the result is converted into double quantity. Then see the effect of a modulus operator. Modulus operator in Java is this one, the same as that of C and C++. Percentage operator, which returns the reminder after performing the integer division. Say x division y. X modulus y. We need to find the value of x modulus y. To find out x modulus y, the integer division x by y is performed and the remainder is returned. This is with respect to integer operands. In case of floating point or double operands, the float or double division is carried out and the remainder is returned. See this example. X is equal to plus 100. Here plus versus unary plus. If not, plus is a binary plus. If and only if it takes the general form. Operator uh, uh, operator is a plus minus star slash modulus. Operands are left hand operand and right hand operand. So operand 1, then operator operand 2. Operator assumes any of the values from the set plus minus star slash modulus. So in this case, plus is the operator and this is the only operand. So this is the unary plus operator. Float y is equal to some initializer is set. Double d is equal to some initializer is set. We do want to find the value of x modulus 11. X modulus 11, right? So 9 times 9 into 11, 99. Remainder 1 is returned. Likewise here, y modulus 25. What is the type of y? Y is a floating point variable and 25 is an integer quantity. So integer division will not be carried out because this is a floating point quantity. Float by int, the result is converted into a floating point operation. So floating point arithmetic division is carried out. Then the equivalent remainder is returned. Likewise here, d modulus 100 minus 2500.02. So in this case, d modulus 100. D is a double type. and 100 is an integer quantity. So finding double by integer, what happens? Double by int is converted into a double type quantity. Then the
So
equivalent
in C or
remainder is
C++, modulus operator works only for integers, no sir?
yeah, that's what I said. Percentage operator is only applicable for the integer operands in C and C++. Where in Java, additionally, the operator is applied for floating point operations, including double. Now have a look into this statement. If you want to write that is plus 1000 modulus plus 750, you cannot write here plus 1000 modulus plus 750. Of course, here plus 750, this is okay after modulus, because here plus is taken as unary plus. So percentage plus 750 is valid here. But however, this is one string. This string is concatenated with some expression. So 1 plus is necessary. If you use another plus, right? Plus 1000. This is taken for the plus operator. So this will result in error. To avoid this error, what you have to do means you need to introduce the proper parenthesis. So I have introduced the parenthesis here, plus 1000 within the parenthesis. Then modulus plus 750. In this case, what will be the result? 1000 modulus 750. 1000 is equal to 1 into 750 plus, what is the reminder?
250.
Yeah, reminder is 250. So 250 is returned there in this step. Here in this case, apparent are of plus and minus. Numerator is 1000. Dividend is 1000. What is the divisor? Divisor is minus 750. So minus 750. What will be the quotient? Quotient is 1000 division minus 750. But
-1.
-1.
yeah, minus 1 not plus 1. Plus reminder is 250. So the sign is the sign is positive, plus 250. Next, in this case, shall we write the minus 1000 this way into what is the divisor? The divisor is 750 plus how to write it?
-250.
-250.
Minus 1.
-1.
Remainder
into
-2.
750. Reminder is minus 250. So here the sign is minus 1. That should be noted out. Minus 250. Then in the last case, both dividend and divisor are of negative quantities. Minus 1000 is equal to minus, what to write? 1 into
+1.
plus 1 into minus 750 plus remainder is minus 250. So here the remainder is minus 250. So what should be understand?
When the numerator is negative, the remainder will be negative.
Yeah, sign of the remainder. This is equal to sign of
Numerator.
numerator, that is dividend. So sign of the dividend, this is same as sign of the remainder, right? So you have to understand this fact. This is the only difference from C, C++ to Java. This can be applicable to floating point operations also. Where in C++, the operator percentage is applicable only to the integer operands. That is the only difference from C, C++ to Java. Then next one, increment and decrement operators.
Sir,
Same as that of C and C++. Yeah.
sir, when we are performing the modulus operator for floating point values, then the remainder should be zero, no, sir, because even the quotient will be zero. So, sorry, quotient will be in floating point, so the remainder should be also in zero.
No. For example, if you write 125.5 modulus 5, what will be the remainder? Quotient is
Quotient is 25.3.
21.1. So, yeah, 25.3.
25.3.
25.3.
1 25.1.
25.1.
25.1.
So this is quotient. So 25.1 into 5 plus the remainder is 0. So in this case,
0.
the result is remainder is 0. The remainder is 0. In case having another quantity, say 100 division, this model is 3.0. In this case, 100 can be written as 33.0. Actually, that is 100.0. 33.0 into 3.0 plus remainder is 1, right? Remainder will not be, remainder need not be 0 in all cases. Remainder is 1.0 as a floating point quantity. Clear?
Sir, the quotient cannot be 3.33, sir. 33.33.
Yeah, 33.33. Yeah, very good. Then, what will be the remainder? 99.9. So
0.1.
remainder is
9.1. Remainder will be 0.1.
0.0001.
Very good.
0.
It need not be equal to, right, 0. Remainder need not be equal to 0, right? So based on the operands, you can get a remainder value. Okay.
Thank you, sir.
Now coming to the increment and decrement operators, same as the of C and C++ languages. Pre-increment, suppose plus plus x. Post-increment x plus plus. Pre-decrement minus minus x. Post-decrement x minus x. That is nothing new. Let me explain directly through this code. Int a is equal to int a comma x is equal to plus 1000. If float z comma y is equal to something. A is equal to x plus plus. What is x plus plus? Post increment operator. Post increment operator first assigns a value of a variable x to the left hand side variable and then it increments by 1. So in this case, first A becomes 1000.
1000.
Am I right? Am I right? A becomes 1000 and x becomes 1001.
1001.
Likewise, yeah, z is equal to y minus minus means the value of y is currently assigned to z and then y is decremented by 1. Likewise, a is equal to minus minus x means first x is decremented by 1 and then subsequently the value is assigned to the variable k. Here plus plus y means y is first incremented by 1 and then y is assigned to the value of z. So after this post increment, after this pre-increment or pre-decrement, both variables can have the same value. But in the case of a postfix operator, what happens means the current value of a variable is assigned to the left-hand side variable, and then either increment or decrement is carried out based on the postfix or prefix operator. Having any queries in this?
No, sir.
We want Java operators. This is a result, right? Similar to C and C++ languages. There is nothing new in these operators. Next, come to another operators. We are moving on to the bitwise operators. There is nothing newly to explain the shorthand assignment operators. As we discussed, int x is equal to 5, x is equal to x star 5 means can be written as x star is equal to 5. Likewise, the remaining operators can be written in the shorthand format. Next, see the different bitwise operators in Java. Bitwise operators can take the operands in terms of a long int, short, char, byte. Where arithmetic operators takes this format: unary operator or binary operator. Unary operator OPR operand, binary operator operand 1 operator, then operand 2. Their operands can be of byte, short, then int, long, float, double. Characters are also included there. Character ch is equal to x. You can write ch plus plus. The next character is assigned to a variable ch. So arithmetic operators can operate on the operands which are of type byte, char, int, short, long. Similar to that, then float and double, right, are also possible. Here the bitwise operators operate on the operands which are of type byte, char, short, int, long, except float, double, and boolean. Boolean are also, right, not included, similar to the arithmetic operators. Now see, these are the bitwise operators supported in Java. This is once complement operator, said to be a tilde operator, right? Similar to a destructor function in C++, a destructor function operator, tilde operator, and bitwise and. What is the purpose of bitwise not? Once complement operator, converting ones into zeros and zeros into ones. Bitwise and, if both the bits are 1, then the result is 1. If any one bit is 0, bitwise and results in 0. Then or, if any one bit is 1, the result is 1. XOR, what is the role of XOR?
Power.
It performs addition.
XOR, what is the purpose of XOR? Function of XOR. X XOR.
If both are 1, the result is 0.
Yeah, both are 1. Result is 0. XOR y is equal to, let's say we write x into y dash, right? Y dash is one's complement, this assume. Then x dash into y. We can write this way. So when both operands are same, 0, 0, or both operands are 1, 1, the result is, what is the result?
0.
0.
0. If the inputs are different, say 1, 0 or 0, 1, whichever it is, then XOR results in a value 1. Similar to that of C and C++ languages, right? I do not want to extend these operations in detail. Then this is a bitwise shift right operation, greater than. This is bitwise left shift operation. Special operator is introduced in Java, triple greater than. Bitwise right shift with zero filling. We see in detail, right? These operators, bitwise left shift and bitwise right shift with zero fill operator. These are simply the shorthand assignment operators related to these operations. Now let us see, before going to see the bitwise right shift, left shift, right shift with zero fill operators, let us see this question. How does Java store integer values? How does Java represent negative numbers, right? How Java stores integer values and how Java represents the negative numbers. This is the basic question. We need to answer this question. Can you answer, right, with respect to C and C++? How C++ stores the negative numbers?
Sir, in C or C++, the For negative numbers, the most significant bit will be either 1, sir.
Now the significant bit is exactly 1, right? MSB is 1. So if the MSB is 1, that indicates that the number is represented in a form of a 2's complement, right? Basically similar to C++, Java also represents the negative numbers in terms of a 2's complement encoding. For example, consider a byte quantity. Byte B is equal to 50. 50 is represented in this binary format, right? This is a 2 power 0, 2 power 1, 2 square, 2 power 3, 2 power 4, 2 power 5. 2 power 5, 32. This is a 2 power 4, 16. So 32 plus 16, 48. 48 plus this is a 2 power 1. 48 plus 2, 50. You see, this is the ones complement representation. Sorry, this is the binary encoding corresponding to the value 50 in the 8-bit register. Total number of bits are 8, right? 8-bit register. Now consider a value, the ones complement of 50. Ones complement of 50 is this way. Converting zeros into ones and ones into zeros. You just have the fundamentals in, right? This is how negative numbers are represented in Java. I do not want to discuss in detail with respect to digital logic fundamentals, right? Just a basic concept, right? It's very simple. For minus 50, how minus 50 is represented in the system? That is the question. For this, right, we are answering. In case minus 50 is represented in the ones complement, right? What we have to do means, carefully understand here, minus 50 in a binary system is this one. In a ones complement, what we have to do means, 1 is represented into zeros and 0 is represented into 1. So this is the ones complement representation. In case of 2's complement representation, what happens? One's complement is added with the quantity 1. So adding this with 1, you will get this value. Here MSB is 1. If the MSB is 1, this is an indication of this is a negative quantity. So this is completely a negative quantity. You have to consider only the MSB, most significant bit 1. So highlighted encoding is to be decoded in a 2's complement format. 1 is assigned minus. So let us decode the value 1 0 0 triple 1 0, right? So decoding along with the MSB, most significant bit 1. This 1 is an indication of minus 1. So remaining numbers are represented in the 2's complement form. So decode with respect to 2's complement. Find the 2's complement of this highlighted number, which means you need to find its 1's complement plus 1. Or in another way, you can consider from right to left and keep first bit, right, where 1 is reached. This is 1. Up to this 1 0, you have to keep. Remaining bits, for example, these things 111 should be converted into 1's complement. So this becomes 0 1 1 0 0. So 0 1 1 0 0 and the last two bits are 1 0. This is a minus 1. So decoding this again, written in the decimal representation, you will get a value 110010 50. 110010 50. So minus 50. So minus 50 is represented, right, in a 2's complement system. Whenever, right, you want to decode it, you need to find out the 2's complement of the by 2's complement equivalent, right? That is a decoding. In that, if the MSB is 1, you can conclude that the given number is in the negative format, right? Sign is negative 1. The thing is, right, why do we need a 2's complement encoding? That is the question. Why not we should have the 1's complement encoding, right? What is the problem in the 1's complement encoding? That we need to discuss. For example, consider this assignment statement. Byte x is equal to 0. A range of a byte variable is minus 128 to plus 127. So representing x is equal to 0 in the 8-bit register, for example, all bits are set to zeros. In case of 1's complement, right, what will happen means 1's complement of these things, what will happen? This becomes all 1, right? So if you decode again in the 1's complement, what will happen means, what is the meaning of this 1? What is the meaning of that 1?
Negative number.
Moses,
Minus.
negative number. Yeah, minus negative number. Minus remaining, I think 7 ones are there. These 7 ones should be decoded in ones complement format. So decoding these 7 ones in ones complement format, 7 zeros. This indicates that, right, you are having a minus zero, right? But there is no concept of minus zero. There is no negative zero in math, right? So minus zero, this is not allowable. In case if the numbers are represented in a two's complement format, means 0 is represented in one's complement as all ones, right? Adding this with 1, right? You will get this quantity. In this case, keeping this as a byte variable, byte occupies 1 byte 8 bits. So, but 1 is stored in the 9th bit, right? So, byte considers only the 8 bits. So, 1 will be lost, right? So, all zeros, these zeros are equivalent to the 0. MSB is 0. So, this is clearly a positive quantity 0. So, we are not having any issue of negative 0, right? Even minus 0 is same as that of 0, right? Minus 0 is same as that of 0, but in this encoding and decoding, we have a concept of minus 0, right? So this is said to be a zero crossing issue, right? So to avoid this, right, what Java does, Java represents the negative numbers using a two's complement encoding, similar to that of C, C++ languages. That is the concept. Now let us illustrate the basic bitwise operators. A byte B is equal to minus 50 and A is equal to minus 50. We do like to perform these operations. This is the ones complement of B and this is the ones complement of B. Should I explain in detail how to find it the ones complement?
Yes, sir.
Do you require that? Okay, 1 minute. Let me connect my open view. These operations are similar to that of C and C++ languages. The bitwise operations and or not. There are no such differences in this. Only thing is you need to represent the value in the corresponding binary format, then find the equivalent ones complement or two's complement. Now let us have byte b is equal to 50. One minute. So having the representation here, byte b is equal to 50. We do want to find out what is the ones complement of b. This is the question. So 50 is represented in this format 1, 2, 4, 8, 16, 32. 32 plus 16, 48. 48 plus 2, 50. So, sorry, that's quantity 32 bit. It's a 2 1, 16 is 1, 0, 0, 1, 0, 4, 4 plus 2, 6, 6 plus 2, 8 bits are there. Understand? This is the equivalent of 50. Now, ones complement of 50, if you represent this operator, for example, here, uh, B is right, the ones complement of B, what happens? Zeros are converted into ones and ones are converted into zeros. So, converting here zeros into ones. This is 1, this is 1. Here next to two bits are zeros, then 1 1 0 1. Now consider the 8-bit register in which MSB, this is MSB, most significant bit. Most significant bit is 1. This 1 indicates that the number is represented in the negative format. Then 1001101, this is in the form of 2's complement. To find out the equivalent integer, we need to find out the decoding of 1001101. To find out the 2's complement, here two ways. One, you need to find 1's complement and then add 1. Otherwise, you keep from right to left and find out where first one is available in 1001101. First one is available at which position? This position. So I am keeping this one as it is. For remaining numbers, simply I am finding 1's complement. So this is 1 is 0, 1, 1, 0, 0, 1. Then one more 1, right? So 0, 110011, right? This is the indication of the equivalent encoding. Now, what is the equivalent number? 1, 2, 1 plus 2, right? 3, 1, 2, 4, 8, 16, then 32. 32 plus 16, right? 48 plus 3, right? 51. 51, the sign is, what is the sign? Sign is a negative 1. So the number represented by which one? 110, 0, 110, 1 is equivalent to minus 51. Understand?
It should be
Understand
minus
or not?
15.
Minus 51. Okay, let us check the result. File operators code. Java operators code. Check what is printed. 1's complement of B is minus 51. Likewise, write int a is equal to minus 50. Here, how to do the trace means you find out the binary equivalent of 50. Then minus 50 in the same way represent, right? Minus 50 in the 2's complement representation. Clearly there MSB will be 1. Then to find out its 1's complement of A, to try to find out the conversion zeros into ones and ones into zeros. And then check, right, in case if the MSB is 1, that is the indication of a negative quantity. Further, you need to decode the remaining bits in the 2's complement format. In case if the MSB is 0, that is 0 indicates that the given quantity is a positive quantity, right? So checking that for minus 50, you can get the quantity. 1's complement of minus 50 is 49. You can easily verify it. Okay. Say yes or no. Having any queries?
No, sir.
Okay. So what to do? What you have to do? You need to represent the binary equivalent of 50. Then since this is a minus 50, right? Represent that in a 2's complement format. Then you will get a MSB as 1. Then convert ones into zeros, zeros into ones. You will get the equivalent quantity in 1's complement form. Since there MSB is 1 in 1's complement, so sure you will get a value 0. MSB is 0. 0, then remaining bits, right? Remaining bits are represented in the same thing. You try to find out the encoding of equivalent, you will get the value, right? The equivalent value. So this way, 1's complement of A for the negative numbers are computed.
Sir,
Then,
what actually what actually 1's complement and 2's complement indicates, sir?
1's complement in some applications, right? We require the use of 1's complement. In some applications, for example, in different image processing applications, right, you can have to perform the masking, some image enhancement operations, some image morphological operations. We need the concepts of the ones complement and the twos complement, binary equivalent. So for that purpose, we need to have these operators, ones complement and the twos complement.
Means what they stay
Next,
at, sir?
what?
Means what actually they indicate, sir? Like one's complement of a number is what, sir? Actually means like it is a negative number, like negative of, or like what it represents actually of a number, sir. One's complement and twos.
Actually, in the complement, right, there are not only ones and twos complement. You can find threes, fours, five, six, etc. Right, nines, tens complements also you can find out. You might have studied in a digital logic paper, right? These are the facilities supported in Java, similar to that of C and C++ languages. In some applications, we need the requirement of the complement, ones complement and twos complement. But actually, why the concept of twos complement or ones complement has been raised in the languages means here how to represent the negative numbers. That is the major issue. In case if we represent the negative numbers in the ones complement, right, then decoding will be a problem for the case of zero. Zero crossing issue is there. For that purpose, two's complement is most conveniently represented. Normally, right, if you store byte b is equal to 50 or byte b is equal to 100, in that state, 100 will not directly be stored as the in your registers, right? Normally, these are represented in the equivalent, the complement representations, binary equivalent, so that you can easily perform the bitwise operations. For that purpose, you need to learn, right, a two's complement and a one's complement. Conveniently, most languages represent the negative numbers in the form of a two's complement include.
Thank you, sir.
Okay, next this one, bitwise AND operator, bitwise or bitwise not. I do not want to extend these things similar to that of the previous one. Here or means what will happen, this is or. If any one bit is 0, no problem. If any one bit is 1, then the A or B, 0 or 1, 1, 1 or 0, 1, both zeros, right? 0, 1, 1 result is 1. Likewise, and right, this one A and B, A XOR B, you might have studied, right? In the same truth table, you need to fix the values for A and B, A or B, A XOR B. Then you need to evaluate. Here, how to evaluate A and B means simply I say A is minus 50, minus 50 is represented in the two's complement format. Be careful. Write the equivalent of minus 50 in two's complement format in combinations of zeros and ones. And write the binary equivalent of 50. Byte B is equal to 50. Binary equivalent of 50. Then perform the bitwise and bitwise OR and bitwise XOR operations. In case if you find any of the MSB is 1, that results in a negative quantity. Remaining bits should be decoded in two's complement format so that you will get the equivalent result. These operators are similar to the C and C++ languages. There is nothing new, right, to explain these operations. Bitwise and bitwise or bitwise not. Okay, so I move on to the next one. Left shift operator. Even the left shift operator works same as that of a C++ language. Apparent, then less than is the bitwise left shift operator, and then you need to specify the number of times. How many number of times or how many left shifts that you need to perform. For example, 1100, another 4 bits, 1111. This is the number. We are performing the bitwise left shift operation, right? So if you perform the bitwise left shift operation one time, what will happen means left shift. What is this, sir? MSB, most significant bit. MSB will be lost. Understand or not? In each bitwise left shift operation, MSB is lost. Then this one is, for example, here I write 1 0 0 4 ones. What about LSB leaves a significant bit? 0 is added. So in each bitwise left shift operation, MSB is lost and new MSB is lost and new LSB least significant bit 0 is added. And in case this is for byte, right, having 8 bits. In case of int operand, integer occupies 4 bytes, 32 bits, right? So after the bit position 31, right, what will happen means, if you perform one time means the 32nd bit, that is MSB, most significant bit, that will be lost. In case of long operand, right, long occupies 8 bytes, right, 64 bits. So in the first time, right, what will happen means 64th bit, right, the MSB will be lost. So in case of byte or short, the left shift operation, normally byte and short operations are promoted to int, right? And then you should be very careful to convert the result again into a byte means or short means, properly introduce the typecasting operation. In case of negative byte or short, right, what will happen means sign will be extended when it is promoted to end, promoted to integer type. For example, see in this example, I explained byte x is equal to 1, y is one byte variable, and a is another integer variable. 1, right, how to represent 1? 1 is represented in the form of 7 zeros and 1, right? 1 represented in the form of 0 0 0 0, then 0 0 0 1. For the purpose of understanding, I left one space after 4th bit. This is byte x is equal to 1 in the 8-bit register, having 8 bits. A, what is A? A is the integer variable. A is equal to x less than 1 means, right? One time you need to perform bitwise left shift operation. So in this stage, right, what will happen means this is the MSB, most significant bit, right? But in the case of integer, 8-bit integer, 4 byte, right, register 32 bits. In 32 bits, you need to consider this way. First byte is 0, second byte is 0, third byte is 0, and this is of course the last byte. So in this case, right, previous bits are completely zeros. So MSB is 0 during the first bitwise shift left operation. MSB is lost, no problem. New MSB is further 0, right? A positive quantity. This 1, right, 1 becomes this position, right? 1 is moved into this new position. So previously the value of x is 1. Now when 1 is moved to the second bit position, what happens? The first bit position, new value 0 is brought, new is 0 is added. So this becomes a quantity 1, right? So one time if you are performing bitwise left shift operation, that is equivalent to multiplication by 2, right? So this becomes 2, then twice you are performing 4, thrice you are performing, right? 1 2 4 8 16 32, etc. In case of, right, you have to predict what will be the value, right, during the 30th shift left operation and 31st shift left operation. I show the result. Java C operators 5. Have a look into this output. 2 4 8 16 32 64 128, right, etc. I am skipping, right, some of the shifts after 10. Then 30 and 31, right, carried out. For 30 and 31, we can see the result. This is the 30 and 31, right? What happens? This is multiplied by 2. When this is multiplied by 2, you will get 2 1 4 7 4 8 3 6 4 8. But this is not the range of integer. Integer ranges from -2 1 4 7 4 8 3 6 4 8 to plus 2, 147, 483, 647, right? So after that, what will happen means cyclically the values are right assumed. Then here, after, for example, byte, here type conversion, byte of x less than 2, 3, 4, 5, 6. What is the range of byte? Minus 128 to plus 127. So after 64, see 2, 4, 8, 16, 32, 64. 64 into 2 is 128. 128 will not be stored in a byte variable because the range of byte is minus 128 to plus 127. After 64, if you multiply this by 2 means, then it becomes the next range, that is the left hand side range, starting range minus 128. Then after minus 128, if you perform the bitwise left shift operation, right, all bits become 0. So subsequently, for any number of shifting operation, you will get a value 0. This is same as the top C and C++ languages, right? Bitwise left shift operation, listen, right, is supported in C and C++ languages. Having any queries?
Sir,
Hmm.
once explain that left shift operator, sir, using that example.
Okay, I explained, don't worry. Yeah, consider this example. Byte b is equal to 1. Suppose int a. Let us find a is equal to b less than 1. What is less than? Bitwise left shift operation. B is the operand 1 is another operand. This 1 indicates that one time you need to perform bitwise left shift operation and the result should be stored into the integer variable. Now, with respect to integer, in integer, 32 bits. This is the first byte, I mean. Second byte. This is second byte. Third byte. Third byte. Fourth byte 1. Let me write in a smaller size. This is last one. I will just look here. This is 1. This is byte 1. Byte. Don't confuse. This is the most significant, right? Byte 1, of course. MSB most significant byte. This is byte 2, byte 3, byte 4. What is A? A is a integer variable. A. B less than 1 means what we have discussed. 1 is what operand? Integer operand. What is B? B is byte operand. All byte short are type promoter to integer 1. So in this case, what happens? So integer arithmetic is carried out, right? Integer mode. So considering 4 bytes, 32 bits. Consider this 4 bytes, 32 bits register. This is a storage representation of a variable. Variable, which one? B. Since B is equal to 1. B is type promoter to integer 1. Now B less than 1 means you need to perform bitwise shift left operation one time. What is this? This is MSB. Most significant bit here. This MSB 0 will be lost, right? This will be lost. Then this 0 is coming to which position? 32nd position, 0. Then this one coming to 31st. Then remaining how many zeros? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 plus 2, 7 bits are there. What is a new MSB? New MSB is 0. Now 7 bits to have one more bit, this 0 is moved to here. So that one byte, most significant byte is over. Likewise, keeping these 7 zeros, keeping these 7 zeros along with this 0, the second byte is over. 4, 5, 6, 7, 8. Then keeping these 7 zeros with this 0, the next byte is over. 3, 4, 5, 6, 7, 8. Then moving these 7 bits, one position left, what happens means 1, 2, 3, 4, 5, 6, 7, 1. This 1 is moved to the second bit position. And what about the first bit position means? First bit position, a new 0 is brought here, new 0. This is the LSB, leaves a significant bit. This is the MSB, most significant bit. New MSB is 0, move from this 31st position to 32nd position. New LSB 0 is brought. Now, the equivalent value 1 0, 1 2 4 8 16. Converting this, what is MSB before that? MSB is 0. 0 means the number is represented in
Positive.
the positive quantity. So converting, decoding this into decimal representation, 1 0, 1 0 is 2. So one time if you are performing bitwise left shift operation, you will get a quantity 2. Then twice we are performing, suppose A is equal to B less than 2. Twice we are performing 1 0, return becomes last 3 bit position. 100, this becomes 1 to 4. Then thrice you are performing A is equal to B less than 3. This 100 becomes 1000. This is 8. Previous leading 3 bytes are completely zeros. Here also leading 3 bytes are completely zeros because this MSB is lost, and these things are moved on to here, so you will get a value of zeros. So 1 2 4 8 16 32 64 etc. The thing is when one is coming to this 31st position here, what happens in the next stage, you should be very careful. That's what here I wrote. When the bits are available, one is brought from 30 bit position. After 31st bit position, what happens means, assuming 31st bit position is 1. Next stage, if you perform bitwise shift left operation, this 1 is moved into where? The 32nd bit position. So MSB will be 1. Remaining bits are something. Now this 1 is an indication of a negative quantity. Remaining bits will be included in the 2's complement system. That's what in the result here. Look here. After 10737 something 824, if you multiply this by 2, actually you will get a 2147 483 648. But that is not the range of integer variable, since we declared A as an integer variable. So in this case, what will happen means all bits are set to ones, right? So ones means what will happen, 32 bits. One means what is the problem? One is the indication of a negative quantity, right? So remaining bits should be represented in the decoded into the 2's complement equivalent. So you try to find out, then finding the 2's complement equivalent, you will get MSB is 1, that is a negative quantity. So minus this quantity, this will be the result. In the case of byte, here considering a 8-bit register, after 64, 2, 4, 8, 16, 32, 64, then actually 128 should be placed. But 128 cannot be stored in this byte variable. Byte of something means here byte of something, right? 128 cannot be represented in the byte variable. So in that stage, what will happen means the MSB, when the MSB becomes 1, 8th bit position becomes 1. That is the indication of a negative quantity. you try to decode the remaining bits in the 2's complement format, you will get the equivalent of minus 128. You try to do the trace, right? After 64, perform bitwise left shift operation one time, right? Sure, we will get the MSB as 1. That is the indication of a negative quantity. Try to decode and the remaining bits in the 2's complement equivalent, you will get a value minus 128. That's what after y is equal to 64, performing bitwise left shift operation in terms of typecasting with respect to a byte operand, right? What will happen means the value is converted to minus 128. 64 becomes next stage minus 128. Understand?
Yes, sir. Thank you, sir.
These are already supported in right C++ language itself. Bitwise left shift operation. There we have right different operands, right? Signed, right? Unsigned, those things. In case right, if you have any problems, right? You try to ask me or you try to message me, right? I will explain your doubt. But the general concept is this one. This is the number